I'm going to be talking about some very surprising to me connections that I have run across between seemingly unrelated areas of recreational mathematics, as you might have gathered from my talk title. And I'm going to be starting with twisty puzzles. So what's a twisty puzzle? Well, Rubik's Cube is a canonical example. There's all sorts of strange variations that you might have seen floating around. And I need to introduce a couple of technical terms about twisty puzzles to start us off. So one is the concept of a bandaged puzzle. This is a bandaged Rubik's Cube. You can see that some of the cubies have been glued together, which prevents certain turns and adds extra challenge to the solving experience. Now, we can always take this kind of bandaged puzzle and unbandage it by slicing through the cuts, and then we restore the Rubik's Cube. Turns out that's not always possible. This is a puzzle called a helicopter cube. Can I have the projector here? Okay, so here we have a situation where the geometry of this thing is such that if you make the turn to a certain angle, you enable a new cut appears, and you can turn an edge when the previous edge is not completely finished. And then you wind up in a state where some moves are blocked. So this is now a bandaged puzzle and it's hard to solve. You can say, well, let's just do what we did with the Rubik's Cube. Let's slice through there and unbandage it. Okay, you can do that. But when you do, that slice, that geometry opens up new moves, which lead to new bandage configurations. And it turns out this puzzle cannot be finitely unbandaged. And the technical term for that in the twisty community is that it jumbles. So I'm actually going to be concerned with 2D twisty puzzles, and in particular, is this the right way up? Yeah. This puzzle here, designed by Doug Engel, who is supposed to be here. I haven't seen him yet, called Gizmo Gears. This is a very challenging 2D twisty puzzle. 2D twisty puzzles are sort of the same. They're these permutation puzzles where you have these cyclic moves that you can make, and you scramble them and you try to solve them. This particular puzzle is a bandaged puzzle, as you can see. If I make this move here that looks like it should turn, it's blocked and it's stuck. And this is actually an extremely difficult puzzle. So the question arose in the twisty puzzle community. We can go back to the projector now. Are there any 2D puzzles that cannot be unbandaged? 2D puzzles that jumble, like the helicopter cube. This is a simple 2D puzzle that is unbandaged. But in particular, people were concerned with whether the Gizmo Gears puzzle jumbles. And I got dragged into this discussion and said, oh, I know how to do that. That's right in my wheelhouse. I'll just write a program to go and give us the answer tonight. And I went and I wrote a program that night, and I didn't get an answer. It took a lot more investigation after that and work on the program. I finally did get an answer. So let's formalize this problem here. You can characterize one of these things by two numbers. One is n, the number of turns it takes to complete a circle. So these things turn in units of tau over n. This is for n equals 5. And you can vary n. N equals 12 is actually what corresponds to the Gizmo Gears that we just saw. It's a bandaged n equals 12 puzzle. So that's one parameter. And the other is r, the radius of the disks. So now we have this very natural mathematical problem, somewhat divorced from twisty puzzles, which is if you're given an n and an r, does this configuration, can it be finitely unbandaged or not? Does it jumble? And so let's look at some specific examples. Here is an n equals 7 case that clearly is already unbandaged. How can you tell it's unbandaged? Well, each disk has 7-fold rotational symmetry, and that means that if I make one turn on either disk, then all moves are still going to be available. So that's unbandaged. Well, what happens as we start to increase the radius? Well, we get this very messy thing here, probably hundreds of pieces there, not a puzzle you would really want to solve, but this is unbandaged. And again, you can tell by looking at the rotational symmetry there, turning it 1/7, and you can still turn anything. So what happens as we keep increasing the radius? Well, we reach a point where it looks like we might be in for some trouble. These lines are about to hit and intersect. What's going to happen? And indeed, it starts to get very messy here. And so now we have lots and lots and lots of little tiny pieces. It's also kind of hard to see what's going on because everything is the same color. So let's investigate that situation a little bit more slowly and deeply. What I'm going to do is zoom in on what we just saw, and I'm also going to introduce some coloring so we can see a little bit more what the underlying patterns look like. I'm not going to describe the coloring rule, but it's very simple. So here we can see the same sort of curved pieces we had as we started to increase the radius. So now I'm going to keep going, increasing the radius further, and zoom in by about a factor of 1,000 at the same time. And we'll see what happens. So you get all of these really pretty patterns that just appear, all this incredibly rich, complex structure that's hiding inside this twisty puzzle. And actually, that takes an enormous amount of computation to do that, I should say. I just got my new Mac Pro last week and was able to make that movie. Okay, but what happens? Let's see, I think I have a slide out of order here. Yeah, so let's zoom back out. This is what it looks like at the radius that we reached at the end of that zoom at the beginning. So here's what the entire n equals 7 puzzle looks like at this radius that's just short of what is actually a critical radius. And flickering there is rendering artifacts. So again, we have this really, artistic sort of built-in structure here. So I used the word critical radius. So what happens at the critical radius? At a certain radius, for any given n, it turns out that there are fractals. So you might be confused by this image because as you see all these little disjoint pieces, this is not a valid twisty puzzle. Where are the lines that divide it? So here I have to explain a little bit about how those images were generated. In order to generate an unbandaged image, what I do is take an arc segment and propagate the image of that arc all around the puzzle under all possible move sequences. And that gives you exactly the cut pattern that you would get if it were unbandaged. So what we have here is the image of a single point along that arc under all possible move sequences. And at a critical radius, turns out this one point generates an infinite image, which happens to be a fractal. So we can see the fractal structure as we zoom in here. And this is already very surprising because this is a very natural mathematical problem. We've already taken out the notions of bandaging and jumbling here, and we simply said, here is a situation. You can rotate like this. You can rotate like this. What happens to the orbit of this point? It goes infinite and generates this fractal. And in fact, there is a very cleanly defined discrete family of fractals. One for every n has its own fractal. So here is this is the n equals 11 fractal because it's G4, G11, of course. N equals 5 fractal has a nice, pretty pattern. However, this does not work for n equals 2, 3, 4, or 6. And this was mysterious for a while, but in hindsight, it's kind of obvious. Those are the numbers for which you can have rotational symmetry in the plane. And these others you cannot. And in the cases where you don't, you get things that are sort of like quasicrystals. And in particular, let's go back. This is a zoom of the n equals 7 fractal again. What happens as we push r past the critical radius? Well, what seems to happen is you generate enough sort of extra degrees of freedom in the motion of the points so that this fractal structure starts smearing out. And as it starts smearing out, and again, this is just the image of a single point, not of the entire puzzle, you start to see these 7-ish symmetries in there. And in fact, this pattern does have the structure of a quasicrystal. And this is clearest if we go back to the n equals 5 case that I showed a minute ago. This is a zoom of the n equals 5 puzzle at r well past the critical radius. And if you are familiar with quasicrystal patterns, you can maybe see that in there already. These parallel lines there called Amon bars that are spaced in ratios of the golden mean. And in fact, if you look at where the grid lines and the sort of grid points are in this image, turns out you can literally put Penrose tiles directly in there. They just exactly fit. And this really blew my mind when I realized this. There's fractals and Penrose tiles hiding inside twisty puzzles. 3 things that are independently interesting, but never in a million years I would have expected this kind of connection. Going back to the original problem, the gizmo gears, that puzzle does indeed jumble and is not unbandageable. Probably. Turns out that this physical version that I have here appears to be just past the critical radius, but depending on the tolerances, it might or might not actually be physically unbandageable if you were willing to play with millions and millions of little pieces. So this was just a really fun mathematical exploration for me that was very much in the spirit of what Martin Gardner would have liked and inspired, I think. Very briefly, you can generalize this problem further we can imagine changing the n's and the r's of the two disks independently. So here is the fractal you get for n equals 3 on the left and n equals 4 on the right. And you can see the threefold rotational symmetry on the left and the fourfold on the right. This is the complete puzzle that generates. Here's n equals 3 and 2 equals 5 in the complete puzzle. If you vary r, then you get an interesting situation where there's no longer a unique one for any pair of n's, because as you change, so here is one for n1 equals 3 and 2 equals 5, but r on the left is smaller than r on the right, and for any given r on the left, there's going to be a critical r on the right. So that gives you a continuous space of fractals for a given n1 and n2. And in fact, you can map out what this space looks like. This is sort of a phase portrait. For any given r1, I've plotted where the critical r2 is there. And if I had longer, I would show you a movie of a slice through this space. It looks like successive slices of a 3D object. So on the upper right of this graph, we have jumbling, and on the lower left, we have non-jumbling, where you can unbandage them. And I will just leave you with a few pretty pictures. This is a zoom of the n equals 7 fractal again. So this is sort of the primitive unit of the fractal here, but with the rest of the puzzle filled in, so you can see where the lines actually go and the pieces actually are. Oh, and let me just point out real quick. See these little teeth here? I can't reach that, but there's teeth in that thing in the middle. It's a gear. We started with gizmo gears. There's gears in there, just by coincidence. Nice. And this is a zoom of the n equals 5 fractal, a little bit short of, or not the fractal, this n equals 5 pattern, a little bit short of the critical radius. Lots of pretty sort of arabesque-like things there. One of the most striking ones I've run across is this one. This is n equals 5, but with two different radii, again, just short of the critical radius. These lines seem to interweave, and you get this very, very definite arabesque-like looking thing there. So I will leave it there. Thank you.